Electrical power systems reach out to every part of our country, to our cities, suburban neighborhoods, industrial sites, and to the most remote reaches of the countryside. The protection, stability, and continuity of these electrical power systems depend a great deal on the efficient operation of substation power circuit breakers. Circuit breakers protect electrical power systems by interrupting excessive currents and by switching source, load, and exciting currents. Because of the critical role of power circuit breakers, it's important to ensure that they're capable of performing their functions from the day they're received and installed through the entirety of their design life and often beyond. The proper operation of a circuit breaker is ensured by thorough inspections and testing. This program will introduce many of the inspections and tests that are typically performed on a new circuit breaker. The details of the inspections and tests will not be shown here, but may be covered in other training. Now, a new circuit breaker can be a breaker that's been shipped directly from a manufacturer. In this case, the breaker is thoroughly inspected and tested at the factory before it's shipped to the customer. But a new circuit breaker can also be a breaker that's been accepted from another source, such as another utility or an equipment broker. It may or may not have been recently inspected and tested. But regardless of whether a breaker is new from the manufacturer or new from another source, it's important to make sure that the breaker wasn't damaged during shipping and that the breaker is properly installed, inspected, and tested before it's put online. In this part of the program, we'll look at the steps involved in receiving a new circuit breaker. First, we'll identify 6 different types of circuit breakers that you might receive, because some inspections and tests apply only to a specific type of breaker. In addition, we'll identify 4 types of circuit breaker operating mechanisms for the same reason. Then we'll look at some of the typical steps of a circuit breaker acceptance inspection. We'll also look at the precautions you should take when unpacking and opening circuit breaker components. There are currently 6 main types of power circuit breakers in use in electrical substations. One of these is the air magnetic breaker, which is typically enclosed in a protective metal cabinet inside a substation control house. The air magnetic breaker uses a puff of air and a magnetic field to stretch and extinguish the arc that forms when the breaker opens an energized circuit. A second type of power circuit breaker is the vacuum breaker. The contacts of a vacuum breaker are enclosed in a sealed vacuum envelope or bottle. Because the contacts open and close in a vacuum, any arcing that might occur cannot be sustained and is usually extinguished quickly. A third type of power circuit breaker is the oil circuit breaker. The contacts of an oil breaker are submerged in an insulating oil, which helps to cool and extinguish the arc that forms when the contacts are opened. A fourth type of power circuit breaker is the gas puffer breaker. In a gas puffer breaker, the contacts are surrounded by low-pressure sulfur hexafluoride gas, commonly referred to as SF6 gas. At the moment that the contacts open, a small amount of gas is compressed and forced through the arc to stretch, cool, and extinguish it. A fifth type of power circuit breaker is the gas blast breaker. Its contacts are also surrounded with low-pressure SF6 gas, but it also maintains a separate reservoir of gas under high pressure. When the breaker contacts open, the high-pressure gas is released through the arc in a sudden blast to stretch, cool, and extinguish it. A sixth type of power circuit breaker is the air blast breaker. In this type of breaker, the contacts are surrounded by compressed air. When the contacts open, the compressed air is released in a forceful blast through the arc to the atmosphere, extinguishing the arc in the process. Each of the 6 types of circuit breakers is operated by one of 4 basic types of circuit breaker operating mechanisms, or variations of the 4 types. One of these is the solenoid operating mechanism. In the solenoid operating mechanism, a solenoid coil provides the force needed to close the breaker's contacts and at the same time compress an opening spring. The compressed opening spring provides the force needed to open the breaker contacts. A second type of circuit breaker operating mechanism is the motor spring mechanism. With this type of mechanism, a motor operates to compress or charge closing springs. The closing springs provide the force needed to close the breaker contacts and at the same time compress or charge an opening spring. In this example, the opening spring is enclosed in a cover pipe near the top of the breaker. The spring is connected to the breaker contacts and the motor spring operating mechanism by operating rods. It provides the force needed to open the breaker contacts. A third type of operating mechanism is the pneumatic mechanism. With this mechanism, a reservoir of compressed air provides the force needed to close the breaker contacts and at the same time charge an opening spring. The opening spring provides the force needed to open the breaker contacts. A fourth type of operating mechanism is the hydraulic mechanism. With this mechanism, pressurized fluid provides the force to close the breaker contacts and at the same time charge an opening spring. The opening spring, which is enclosed in a cover pipe near the top of the breaker, provides the force needed to open the breaker contacts. Because of the obvious differences between types of circuit breakers and types of breaker operating mechanisms, some inspections and tests apply only to one type of breaker or breaker operating mechanism. But there are many tasks that are basically the same for all types of breakers and operating mechanisms. One of these is a circuit breaker acceptance inspection. A circuit breaker acceptance inspection is an inspection of the breaker that's performed when the breaker is received. The main purpose of an acceptance inspection is to identify any damage or evidence of rough handling before you accept the breaker. Many breakers, particularly smaller breakers, are shipped fully assembled. Others may be shipped with some of their components packed in separate crates. When the breaker is received, and typically before it's unloaded, the exterior of the breaker is checked thoroughly for damage or evidence of rough handling. For example, dents or creases in the breaker may result in leaks or structural weakness. Bent lifting ears or wings may have been caused by improper rigging that could result in internal damages. The components inside the breaker operating mechanism cabinet are also inspected. Common problems include broken gauges, leaking fluid, cracked fuse boxes, and other obvious damage. Such damage may indicate that the breaker has been dropped, which could also result in damage inside the breaker. If a breaker is large enough to be entered, the components inside the tanks are thoroughly inspected for damage. Be sure to follow the proper safety precautions for entering a confined space. It's also important that moisture and dirt not get inside the breaker, so a breaker should not be opened if the weather is rainy, snowy, humid, or windy. If a breaker is delivered with some of its parts packed separately in crates, the crates should be checked for damage when the breaker is received and before the crates are unloaded. A cracked or broken crate might be a clue to damaged parts inside the crate. If damage is suspected, the crating should be removed enough so that components inside can be inspected. The crating and any other packing material should be removed carefully to avoid causing damage. Porcelain bushing should be handled with special care so that they're not cracked or chipped. In addition to being checked for damage, all parts should be checked against the packing slip to make sure that no parts were inadvertently left out of the shipment. If any damage is found during the inspection, or if any parts are missing, a claim should be filed immediately with the company that delivered the breaker. The breaker manufacturer should also be promptly notified. By performing an acceptance inspection and reporting any damage or missing parts, you help to ensure that your company gets what it pays for, a circuit breaker in good condition and with all its parts. But an acceptance inspection doesn't ensure that the breaker is ready to be put in service. It still needs to be properly installed, re-inspected, and tested. In the next part of this program, we'll look at circuit breaker installation. But for now, read the material in your text on receiving and answer the questions provided. After you've received a breaker and determined that it's not damaged, and that all the parts are there, the breaker can be installed. Teamwork and attention to safety are needed to complete an installation without damaging the breaker or risking injury. Now, the detailed steps for installing a breaker can vary depending on the manufacturer and the size and type of the breaker. You'll need to follow the instructions in the manufacturer's manual to ensure that these detailed steps are meticulously carried out. In this part of the program, we're going to look at some of the general steps involved in installing a circuit breaker. Some breakers, such as draw-out type air magnetic or vacuum breakers, require very little in the way of installation. Typically, these breakers and their enclosures are designed so that the breakers can be interchanged. Wheels on the breakers and a portable fifth wheel make it possible for one or two people to remove or install a breaker as needed. Other breakers, such as this gas puffer breaker, require more planning and care to move and install. A breaker like this one is usually moved by lifting it, using slings and a crane. The slings are typically connected to eye bolts or lifting hooks on the breaker that are provided specifically for lifting. The weight of a breaker is often unevenly distributed, so the manufacturer's instructions may specify that the slings to the heavier side of the breaker should be shorter than the slings to the lighter side of the breaker. The breaker is hoisted and moved carefully so that it isn't tipped over, dropped, or knocked into other equipment or structures. Some breakers may have additional braces or shipping framing that were installed to reinforce the breaker during shipping. The additional braces are typically left on until the breaker is set on its pad, positioned, and bolted down. When the breaker is placed on its pad, it's set down carefully to ensure that it doesn't tip over and that it lines up properly with its anchor bolts. Then the breaker is secured to its foundation. Within a reasonable time after the breaker is secured, it should be connected to station ground, especially if the breaker is installed in an operating substation where it may pick up induced voltages. When a circuit breaker is delivered with its bushings packed separately, the bushings must also be hoisted into position using slings and a crane. The procedure for lifting and moving a bushing can vary with the size and type of bushing. For example, the bushings in these crates are large oil-filled bushings for the 230 kV breaker behind the crates. The bushings are very heavy. Each bushing contains a mounting flange with lifting loops on opposite sides of the bushing. To lift the bushing and install it in the breaker, slings are attached from the lifting hook of a crane to the lifting loops on the mounting flange of the bushing. In addition, a block and tackle is connected between the top of the bushing and the lifting hook of the crane used to lift the bushings. The bushing is lifted clear of the crate using the slings. Then the block and tackle is adjusted to give the bushing the proper tilt so that it can be easily inserted into the breaker. The bushings for this gas breaker are installed using a completely different procedure from the one followed for the oil-filled bushings. The bushings for this breaker do not contain oil, and they are relatively light compared to the oil-filled bushings that we just looked at for an oil breaker. The manufacturer of this breaker and its bushings recommends that a nylon sling be placed around the bushing between the 38th and 39th petticoats, counting down from the top of the bushing. Because the bushing is light, lifting the bushing in this manner shouldn't damage it. A shipping cover protects the bottom of the bushing until it's lifted clear of the ground. Proper placement of the nylon sling will give the bushing the proper tilt needed to install it in the breaker. After a breaker is installed and assembled, it must be thoroughly inspected and tested before it can be put in service. We'll look at a post-installation inspection in the next part of this program. But before continuing, read the material in your text on circuit breaker installation and answer the questions provided. We've learned that breakers are inspected and tested at the factory. We've seen that when the breaker is received by the customer, it's carefully inspected, installed, and assembled. Despite these inspections and checks, the breaker still may not be ready to put in service. Parts can be damaged, moved, disconnected, or jarred out of adjustment during any of the previous steps. So it's a good practice to thoroughly inspect and test the breaker after it's been installed and before it's put in service. In this part of the program, we're going to look at common checks that are made during a post-installation inspection. These include mechanical checks of the circuit breaker and mechanical checks of the breaker's operating mechanism. Keep in mind that these checks may also be performed during maintenance of circuit breakers that have already been in service. An important part of inspecting a breaker prior to putting it in service is documenting the status of the breaker. This is important for a couple of reasons. Thorough documentation of the status of a new breaker before it's put in service establishes benchmarks for future inspections. All future inspections will be compared to the information documented at this time. In addition, the documentation from this inspection, as well as from future inspections, provides the type of information needed to develop and carry out an effective planned maintenance program. The documentation should include the status of each inspection item. Here are some of the typical mechanical checks of a circuit breaker. Ground cables are inspected for cuts or breaks or other signs of damage, and to ensure that ground connections are secure. The breaker's foundation bolts are checked to make sure that the breaker is securely bolted to the foundation. The bushings are inspected for any chips or cracks. Oil circuit breakers are checked for any signs of leaking around access covers, pipe fittings, bushings, and joints. Gas-insulated breakers are checked for proper gas pressures. All control wiring is inspected to make sure that it's not damaged, that all wire insulation is intact, that all wires are properly connected, point to point, according to the wiring diagram, and that all wire terminations are secure. In addition to mechanical checks of the breaker, a number of mechanical checks are made of the breaker's operating mechanism. For your safety, the operating mechanism must be disabled or blocked so that it cannot operate while you're checking it. All hardware, such as nuts, bolts, washers, cotter pins, and snap rings, is checked to make sure it's secure. The plungers on all control coils are checked by hand to make sure that they move freely. The dashpot rod on each dashpot is moved by hand to make sure that it too moves freely. Latch wipe is checked. Latch wipe is a measurement of how much of the surface of a latch rests against a roller or other component to hold the operating mechanism in a given position. Latch clearance is also checked. Latch clearance is the amount of clearance needed for a latch to consistently drop into a given position. The bell crank position is measured, typically when the breaker is closed. The bell crank is a mechanism that changes the direction of mechanical motion, such as changing the vertical motion of an operating rod to a horizontal motion. Operating rod position is also measured with the breaker closed to ensure that the rod is in the proper position. Some operating mechanism checks apply only to a specific type of operating mechanism. For example, the compressor on a pneumatic operating mechanism is checked for proper oil level. It's also checked to make sure that the air filter is clean and properly installed, and that the compressor drive belt isn't damaged and is adjusted for the proper tension. The air supply system in the pneumatic operating mechanism is checked for leaks. For a hydraulic operating mechanism, the hydraulic fluid system pressure is checked, and the hydraulic fluid level is checked. Then, for both pneumatic and hydraulic operating mechanisms, the operation of various pressure switches is checked. Pressure switches typically include a compressor governor switch, a low-pressure alarm switch, and a low-pressure cutoff switch. Both the pneumatic and hydraulic operating mechanisms are also checked for their operating capacity. Operating capacity is defined by how many times the breaker can be operated without recharging the compressed air tank in a pneumatic mechanism or the hydraulic fluid system pressure in a hydraulic mechanism. The mechanical checks of a breaker and its operating mechanism can be quite detailed and lengthy, but each item must be carefully checked and documented according to the manufacturer and company instructions. Remember, you want to make sure that the breaker will work properly without failure when it's put in service. For the same reason, various tests are performed on a circuit breaker before it's put in service. We'll look at proof tests when we continue in the next part of this program. But first, review the material in your text on circuit breaker post-installation inspection and answer the questions provided. Once a circuit breaker and its operating mechanism have been thoroughly inspected, and it appears that the breaker is ready to be put in service, a few tests are recommended to ensure that the breaker will function as it's designed to function. These tests, which are generally referred to as acceptance or proof tests, are what we'll look at in this last part of the program. In general, proof tests are the tests that are performed on a new circuit breaker to make sure that the breaker has been installed without damage, that it complies with the specifications, and that it meets its design intent and limits. Proof tests also establish a benchmark for future tests. The same tests that are performed on new circuit breakers are also typically performed during maintenance and testing of breakers that have already been in service. As with the post-installation inspection, proof tests should be thoroughly documented. To provide meaningful comparisons with future tests, it's important to document actual measured test values rather than just noting if the test results were within prescribed tolerances. One proof test that is usually recommended by breaker manufacturers is the time travel test. The purpose of a time travel test is to determine if the breaker can make and break circuits under normal load conditions, and if it can interrupt circuits under fault conditions. In principle, the test is performed by operating the breaker and measuring its electrical and mechanical performance. There are two main parts to the test: timing and travel. For the timing part of the test, contact test cables are connected from the test instrument across the breaker's contact terminals to determine when the breaker contacts open and close. For the travel part of the test, a cable is connected from the test instrument to a mechanism called a transducer. The transducer is connected to the breaker's operating rod to detect the movement or travel of the operating rod when the breaker is operated. When the breaker is operated for the test, the time travel test instrument draws lines or traces on a moving sheet of paper. These traces provide a good deal of information about the operation of the breaker, including contact make and break times, operating rod travel distance, operating rod travel velocity, and a variety of other circuit breaker operating characteristics. The time travel test is typically performed for several types of breaker operations. The traces for each operation can be analyzed to determine how the breaker is performing in comparison with the manufacturer's specifications. If the breaker's performance doesn't fall within acceptable ranges, the breaker will need to be properly adjusted before it can be put in service. Another proof test that's often recommended is the contact resistance test. Resistance in the closed contacts of a circuit breaker can have a number of causes, including arcing deposits, a loose or incomplete connection, or pitting from repetitive arcing. Contact resistance creates heat that can reduce the life of the contacts and may even lead to breaker failure. The purpose of contact resistance testing is to detect unacceptably high contact resistance levels before failure occurs. In principle, the test is performed by passing a direct current through the closed contacts of the breaker and measuring the voltage drop across the contacts. The test instrument uses the current and voltage values to calculate and display the contact resistance. If the contact resistance exceeds an acceptable limit, the contacts may have to be cleaned or replaced. A third common proof test is the insulation resistance test. When the circuit breaker contacts are open, the breaker's insulation should provide a high resistance to prevent current from flowing. The purpose of insulation resistance testing is to detect unacceptably low levels of insulation resistance before poor or weakened insulation leads to a failure. In principle, the test is performed by applying a high DC voltage to one of the breaker's bushing terminals with the breaker's contacts open. Then, leakage current is measured either to ground or across the open contacts to the other bushing terminal. The test instrument uses the DC voltage and leakage current values to calculate and display the insulation resistance. If the insulation resistance is lower than an acceptable minimum, the cause of the low insulation resistance must be identified and corrected. A fourth proof test that may be performed on a circuit breaker is the power factor test. The purpose of a power factor test is to determine the condition of the electrical insulation of the circuit breaker. In principle, the test is performed by applying a high AC voltage across the breaker bushing terminals. With the breaker contacts open, leakage current is measured across the open contacts in both directions. With the contacts closed, leakage current is measured across the closed circuit to ground. The test instrument measures milliamps and watts. These values are documented. They're also used to perform calculations to determine the power factor of the breaker insulation. If the power factor is not within an acceptable range, the breaker may have to be closely monitored or retested on a regular basis, or the bushings may have to be replaced. Regardless of the test results on the breaker, a power factor test is also typically performed on each of the bushings and on an oil sample if the circuit breaker is an oil breaker. A fifth proof test that sometimes is performed on a circuit breaker is the high pot test. The purpose of a circuit breaker high pot test is to check the condition of the electrical insulation of the circuit breaker at its rated voltage. In principle, the test is performed by applying rated AC or DC voltage across the breaker bushing terminals. With the breaker contacts open, leakage current is measured across the open contacts in both directions. With the contacts closed, leakage current is measured across the closed circuit to ground. The test instrument indicates the applied voltage and measures and indicates any leakage current. If the circuit breaker insulation is weak, the stress of the applied rated voltage may result in a flashover or an insulation failure. If this happens, the test set automatically shuts itself off. If the test instrument indicates that leakage current exceeds an allowable level, the cause must be identified and corrected. If the insulation fails during the test, the failed components must be replaced. The tests that we looked at here may not be the only ones that your company requires prior to placing a new circuit breaker in service. For example, the oil that will be used in an oil circuit breaker may be tested for moisture and contaminants. The gas in a gas-insulated breaker may be tested for moisture content. Current and potential transformers on the circuit breaker may be tested, or the breaker may be tested to see that it operates properly in conjunction with associated relays and alarms. What we've looked at is an overview of the typical inspections and tests that are performed on a new circuit breaker from the time it's received till just prior to the time that it's put in service. This should serve as a good foundation as you learn the specific procedures that your company follows and as you learn how to use your company's test equipment when inspecting and testing new circuit breakers.